Okay, so now we will start. Can you see my screen?
Yes, sir.
So this is so. Can you mute yourself? Okay. So today we will talk about the tutorial of week 4, and as well as we will discuss about some topics covered in this week. Okay, and I also cover if you have some doubts, anything. Okay, so now we will come to the tutorial 4. So question number 1 is given like in Young's double slit experiment, hello Sudham, hello. Okay, so in slit experiment, so what the condition of minimum radiance is obtained. So I think you all have read this Young's double slit experiment, right? Hello.
Yes, sir.
So do you know what is the condition for minimum radiance in Young's double slit experiment?
Yes, so irradiance is calculated by I is equal to I1 plus I2 plus I12, and I12 is given with 2 root I1 I2 cos a phase difference.
Yeah.
So depending on phase difference, it can be either positive or negative for that. Yeah, that factor.
So for
So
phase
that
difference, our options are, you just tell me by calculating, plus minus 2 pi, comma plus minus 4 pi,
4 pi. Yeah.
or the second one is for phase difference 0, comma plus minus pi by 2 plus minus 3 pi by 4 and so on. Our third option is plus minus pi and plus minus 3 pi phase difference, and fourth is none of these.
Yes. So it's A.
A.
Yeah, the first one.
First one. Let's see. The minimum radiance is found when the path difference, that is, I am talking about term of path difference, is what? lambda by 2. I am right or not?
Yes, sir.
Half a wavelength. Okay. So phase difference will be around 2 pi by lambda into delta x. So minimum radiance is difference, path length difference is lambda by 2. So 2 pi by lambda is equal to lambda by 2. So it will be around pi. Okay. So odd multiple of pi gives us the minimum radiance, not the even multiple. Even multiple of pi gives
But,
us the maximum radiance, right?
but sir, in the question they're asking for maximum, right?
No, no,
Uh,
this is minimum.
oh, sir, I thought in the okay, in the test, the assignment at least it was maximum variance.
Okay, okay, okay. So I am not solving the exact assignment, but based
Okay,
on
okay.
that, the different questions may be there. So please read carefully.
Yes, sir.
Okay. So this is part difference of pi or odd multiple of pi. Okay. So our right answer will be here, third one.
I'm not sure.
Okay. This is the previous year's assignment. I am not allowed to solve your assignment of this year. That's why I am doing these things.
All right, sir.
Okay. So our question number 2 is two coherent orthogonally polarized plane wave interferes. Interferes. The interference pattern thus observed will be straight line fringe, uniform illumination, circular fringes, or none of these. The interference, just think about that. Your options are 1 straight line fringes, option 2 is uniform illumination, and circular, or none of these.
So they won't have any fringes, right?
क्यों?
Because since they're orthogonal, they won't have any. They won't interfere with each other.
Why?
Uh, because there won't be any component in the same direction. They'll just like pass through each other.
Okay. Yeah. So answer will be uniform illumination or none of these.
Um, I I think uniform illumination.
Yes. So it will be uniform illumination. Okay. So
Okay, sir.
answer 2 will be correct. Similarly, question number 3 is the pattern observed plane wave interference with a cylindrical wave will be. Okay, so the pattern observed when a plane wave interference with a cylindrical wave will be. Think about that.
So what are the options?
The same options are there as above: straight line fringes, circular fringes, uniform illumination, or none of these.
Um, I'm not sure. I don't think it will be uniform illumination, but I'm not sure between circular and straight line fringes.
Okay. So, and what is the interference pattern between plane wave and plane wave?
Uh, that's straight lines, right?
Straight line. Okay. So in this case also there will be straight line. The reason is like if we have the cylindrical wavefront, right? But this this like this plane will be something like that, na? And at the very far away from the cylindrical axis, this will work as a plane wave, right? So the interference will be happens in this case with only the cylindrical wave and in the plane wave interference manner. So the shape will be straight line fringes. Okay.
Okay, sir.
And actually this plane wave interference is not exactly straight line, but it is a hyperbolic shape. If you have read this Young's double slit experiment in little bit more detail, the shape of fringes will also come in the topic. So in that case, if you calculate the shape of fringes, this is not perfectly straight line, this is hyperbola. But because our screen is very limited area, right? So that's why it's shown as a straight line if we approximate for a smaller region of the fringe.
All right. So circular waves are mostly involved when there's a plane wave and a spherical wave involved together, right?
Not really. Let me explain in this way. See, the shape of fringes is mostly happens when, like, in Young's double slit experiment, this is your screen, okay, and
Yes, sir.
these two are slits, okay. So fringes forms like that, and in this direction, uh, out of plane at this point, if you straight line, the path difference will be same for all this path, right? Understood or not?
Yes, sir. Yes.
So the fringe will follow the pattern of the equal path difference, right?
Yes, sir.
So here the line, if the screen is like, if screen is like that, the fringes will be something like that.
Yes, sir. Yeah.
Okay, because the constant path difference will follow this path only. But now I am changing the orientation of the slit. Orientation of the slit is something like that, and our screen is like that. What will happen?
Mm,
So in this case, this will follow this path. This path is equal delta x.
okay.
Can you calculate this thing?
Okay.
The path at which the delta x is constant. So this will be circular. So in this case, we will find the circular fringe.
So how do I calculate this, sir?
Hmm?
How would I calculate this path difference?
Part difference, right? So part difference is same, like screen is somewhere here, and the path difference will be, this path will be equal, right?
Yes, sir.
So if you calculate this angle theta, like
Okay.
this
Got it, sir.
theta angle,
Yeah.
then this much is the path difference only, and we know this distance a, right?
Yeah. Yeah.
That all these things are same, but the thing is, what path is follow this delta x, equal delta x, like same delta x, which path is follow, the fringes will be in the same shape, like that.
Yes, sir.
Suppose
All
screen
right.
is putting like that, then this path will be like that. So this will be your circular fringes. If you tilted this something like that, then it will be little bit ellipsoid or something at the different type of fringes. Okay, so you
Okay.
can say that uh, Newton's ring you have listened or you have heard the name Newton's ring.
Newton's rings. Yes, sir.
Yeah, so that is also a circular fringes.
Yeah.
Why?
Not sure, sir. Actually, I don't remember.
Okay, so in the circular fringes, how Newton's ring fringes is formed? So there will be some slip or curved slip is there, and this is the plane surface. Okay, this is your whatever you call a lens or something. Okay, so here is a thin film interference. So whatever thin the rays going here, this much part difference is happening, right? This is here and this is, so this the constant delta x will follow the circular path. That's why it is here circular fringes, because light coming from here and here to here. So this much part difference is due to this ear gap between lens and the plane surface. Okay, so whatever the thickness is equal, where is the thickness is equal to this one, that will be one fringe. So that is, if your lens is circular like that, so the, the fringe will be like that. You understood or not?
Okay. Yes, sir. Yes, sir.
You can imagine, if your lens curved lens, uh, if your curved lens is like that, okay, and here is some plane plane wave, so you, this much thickness is along this one, right? Constant thickness
Yes, sir.
will be along this path. So fringes will be only, you can see fringes like a circular path like that. So it
Like
depends on the,
concentric circle. Yeah.
yeah, concentric circle. So this is discussion about the shape of fringes. You can also can search on Google shape of fringes in different pattern, different like
All right, sir.
fringe pattern. You will find all these type of concepts. Now next question I have to solve in Young's double slit experiment. A laser light passes through two identical and parallel slits. Laser light passes through two identical parallel slits are 0.5 mm apart. Okay. Interference fringes are seen on screen kept 1 meter away. Okay. So I can just draw a diagram. This is your screen. Okay. Light through two identical and parallel slits. So this is slits. Distance D is given 0.5 mm, and the distance of the slit, and this is 1 meter away from the plane of the slit. At the screen, the adjacent interference minima are observed to be separated by, so this fringe width is given here, beta is 1.2 mm. Okay. So the wavelength of light, you have to find the lambda. Can you find?
Yes.
Yeah, just solve it and then I will solve. Your answers are 600 nanometer, 550 nanometer, 658 nanometer, and 500 nanometer.
So it's A, I think.
Sorry,
I think it's A.
it's A. You think or you solve?
I mean, I saw, sir. I may be wrong,
Okay,
sir.
okay. So this is given the fringe width, right? So fringe width formula is something like lambda d
D by small d.
small d, right? So this lambda will be d beta by d. This is 1.2 into 0.5 divided by 1 meter into 100 centimeter and 10 millimeter, right?
Yes, sir.
Okay. So this will be 12 पंजे 60 that you are right. 6, this is 0.6 into 10 to power minus 3. So it will be 600 nanometer.
Yes, sir.
This is in mm, right?
Yes, sir.
Now this is 600 nanometer. Next question is given: two coherent harmonic light the amplitude of 2 unit, okay, and 3 unit interferes at some point P on a string if their electric field vector associated with two harmonic waves are parallel. So the electric fields are parallel, okay. So what have to calculate, then uh, the ration of maxima to minima intensity, that is I max by I min at the screen will be. How can you solve it?
Um, we can the maxima would be so the intensities would be this square of amplitude.
Yeah,
So you get 4 and 9, and then
square.
for the maxima you'd add the I1 to, because cos
So
delta would be 1
I max will be I1 plus I2, right?
plus I1 to
Plus,
plus I1 to interference factor.
so this maximum will be I1.
Yeah, it'll be 2 root I1 I2 cos delta.
Okay, let's start with the amplitude term, right? We write 1 like E1 sine omega t plus 5 and E01, and E2 is E02 sine omega t plus phi 2, right? When these two interferes, in my first class I solved this. The resultant amplitude will be E1 plus E2 plus 2 E1 E2 cos theta, right?
Yes,
So
sir.
ER max will be E1 plus E2 whole square, and ER minimum will be E1 minus E2 whole square. Do you know how can I write this these sandwich?
Uh,
See, ER maximum कब होगा when cos theta is equal to 1, right?
yeah,
This
and
is max
minimum will be when cos theta is minus 1.
minus 1. So when this will be minus 1, this is minus. So no, I'm writing something. Ah, this is the formula. So a square plus b square plus 2ab. This will be a plus b ka whole square, right? Similarly, if theta is cos theta is equal to minus 1, then a square plus b square minus 2ab means a minus b ka whole square, right? So
Yes, sir.
I max will be e square, right?
E square
E
and the
max
time
square,
average of.
e max square. So it will be
Yes.
e1 plus e2 to power 4. Similarly, I min is equal to e square min is equal to e1 minus e2 whole square, sorry, whole power 4. So these are amplitude, okay, of individual
Yes, sir.
waves. So these are given amplitudes 2 and 3, right? We have to find
Yes,
I
sir.
max by I min. So I max by I min,
I think I got the answer, sir. Is it 25?
I think so. So this will be 2 plus 3 power 4 and 2 minus 3 to power 4. So it will be 5 to power 4, not 25 I think. This will be around, this will be 25, but sorry, यहाँ पे e square
Sir,
होता है.
yeah, they're already e
Yeah.
square, right? So it won't be e to the power 4.
So then it will be,
E1 plus e2 square and e1 minus e2 square.
this is e square, so we can write it as I max, right? This is at I min.
Yes, sir.
So this will be square, square and square. This will be 25 answer. Okay.
Yes, sir.
Do you have any assignment question like that?
I think there was a similar question in the previous week,
Okay.
but yeah, not exact same.
Okay. So two harmonic light wave with amplitude of 1 and 2 unit, and the phase difference is pi by 6. Okay. Interfere at some point P. The resultant intensity you have to find. Your answer options are 2, B is 7, C is 1, and D is 8.5.
So it's D.
It's D, right?
Yes, sir.
How you calculate?
I had the amplitude, so I can extract the intensity from that. Intensity will be 1, 4, and then I just can put it in the formula, and I already have the phase difference. So it's just calculating over there.
But here this is I max and I min, right?
Yes, sir.
And here they have given this phase difference is pi by 6.
Yeah. So cos pi by 6 would be 3 by 2. Mm.
Yeah. So your I is equal to I1 plus I2 plus root I1 I2 cos theta, right? So this
Uh,
also,
I think it's 2 root I1 I.
yeah, 2 root I1 I2. Yeah. So your is 1 and 4, I1 and I2. So this will be 1 plus 4 plus 2 into root 4 and cos pi by 6. So cos pi by 6 is how much you are telling? Cos pi by 6? is 30 na, cos 30 is under 3 by 2. 7147 रहता है ना अंडर रूट 3 की वैल्यू.
Yes, sir. It's approximately 0.7.
So 1.27 3.4, 5 plus 3.4 is equal to 8.4 or 8.5 you can say. Question number 7 is, in Young's double slit experiment, slit separation and slit to observation plane distance are decreased by half. The fringe width will become. Okay. Question is, Young's double slit experiment, slit separation and slit to observation distance are decreased half. The fringe width will become. Answer is 4 times. B is double.
It's I think it's double, sir.
And D is no change. In my opinion, there is no change.
So won't it be doubled because wait, the fringe width is equal to lambda into like the total distance divided by the slit separation
Lambda is equal to lambda d by
by small d.
small d. D is also half, D is also half. Means,
Oh, I'm sorry. I didn't see that they're both decreased by half.
yeah.
Okay. All right.
So there will be no change.
Yes, sir.
Now, question number 8 is given that if white light is used in Young double slit experiment, the correct statement for interference bands will be, if white light used in Young double slit experiment, correct statement. So statements are, no band will be obtained, B, many bands will be obtained as the case of monochromatic light, but they will be colored except the center of the central band, which will be white. So many
Yes, sir.
bands
I think that's one. That one's correct.
will be obtained as in case of monochromatic light, will be colored. Okay, and C statement is very few bands, but they will be colored. इसका dongle शायद उधर लेके गया फिर. They will be colored except the central band which will be white. And D is many bands will be obtained as in the case of monochromatic light, but all of them will be white.
Sir, only the central fringe will be white, right?
Yeah. Think about all four. Which will be more correct?
Sir, it's either between B or C because only the central fringe will be white, but I'm not sure whether there'll be many bands or few bands.
Okay. So there will be central width will be always white. Okay.
Yes, sir.
So central band will be white is there also. All of them will be not white. So this is certainly wrong.
Yeah.
Okay. And many bands will be obtained case of monochromatic light, but they will be colored. Yeah. क्योंकि what will
I
happen ना in all fringe width will be different for different wavelength. Okay. So when they will merge, then they will be like a rainbow. All fringes will be like a rainbow, but the central fringe will be like a
White.
white. Okay. So that
Yes, sir.
will be the correct one.
Okay, sir.
Okay. Now question number 9 is, in double slit experiment, interference arrangement, one of the slit is covered with a thin mica sheet. Thin mica sheet. Okay. And the refractive index is 1.5. Separation between the slit is 2 mm. Okay. And the distance between slit and screen is capital D is given 2 meter. Due to the introduction of the mica sheet, the central fringe gets shifted by 0.5 mm. This is the shift of central fringe. So we have to find what is the thickness. What is the thickness of alpha sheet. This is a good question.
Alright, so yeah, calculate. So the refractive index is 1.5, right?
Yes, 1.5. Do you know the formula for this one?
Yes, sir. I think also. So delta y will be capital D by small d mu minus 1 into t. So I got 10 to the power minus 3 for t, but I don't know whether it's correct because I might have
10 to the power
calculated it fast.
minus
3.
3 means 1 micrometer, right?
Yes, sir.
Yeah, it
So
may be right.
1, yeah.
Yeah, it may be right. So, what you can you drive this? How can we get if we need this?
So they've given us the shift in the central fringe. So that's delta y, and we know that delta y is equal to d. That's the distance between the and then divided by the separation of the
Delta
slit.
y equal to, sorry,
Capital D divided by small d,
capital D divided by small d
and into mu minus one
into mu minus 1
into thickness t.
into thickness t. Lambda
So
will
from
also
there
be
we
there.
can. So all the variables are present in the
So,
question.
lambda should also be there, right?
No, isn't it independent of lambda because we're taking delta y and not y?
So, how we can find this delta y?
Uh, we can take m plus 1 lambda minus m lambda and then
M plus 1
subtract it
m plus 1
and then
lambda
find the difference.
minus m lambda.
Yes.
Then it also comes lambda, right?
Yeah, lambda will come here. Um,
In this question also the wavelength is not given. I am surprised. what is the basic concept of this one? See, in Young's double slit experiment, okay, in
Yes,
one
sir.
case this is yn, okay, and this is at point P. So path difference between these two lines we consider is a sin theta, right?
Yes, sir.
So this is your delta x. So this delta x is equal to a sin theta, or this theta we consider very less, then this sin theta is equal to tan theta is equal to theta, right? So from the tan theta terms it is coming tan theta, theta is equal to tan theta is equal to yn divided by capital D, right? So this delta x will be a is, I am considering this D, sorry if you are confusing. So this is D, okay. So this will be d theta, and d yn is equal to yn upon capital D. Am I right?
Yes, sir.
Yeah. So this will happens because, and this, but they are giving the central fringe, right? So central fringe will be happens when, okay, so this is without mica, so I am calling it 1. If there will be some mica sheet of thickness t and refractive index mu, then additional part difference will be coming here, right?
Yes, sir.
So if I considering this in this one, then the total path will be OP minus O dash P, right?
Yeah.
And this will, OP will be, in comparison to this one, this will be mu minus 1 into T plus distance in air, okay.
Yes, sir.
Distance को I am calling EOP dash, okay. And minus this will be AP plus A sin theta, right? So this AP and OP
Yes,
we are
sir.
considering almost equal, then this the part difference will be D sin theta plus mu minus 1 into T equal to delta x, right? So this will be
Yes, sir.
delta x 2, yeah. So we have to, I am just calling here theta, not yn, okay. So I consider it later. So it is giving that delta x1 minus delta x2, we have to consider this by n here only. So this will be yn, here this yn is 0, right? So delta x is equal to 0. And here dyn upon capital D minus mu minus 1 into T, this will be equal to 0. So yeah, this is again delta x2. So delta x2 for central fringe, this there is 0, right?
Yes, sir.
Central fringe 0. So delta x should be 0 there or here also, right? But in that we will write here, I think. Then there will be no lambda here. Okay, understood why this lambda is not coming here.
Sorry, sir, my connection keeps going out.
Okay, okay. So I am saying here that why lambda is not coming, because lambda में y, if you are considering yn in absent of mica seed, and again yn2 in presence of mica seed, right?
Yes, sir.
So yn in absence of mica seed, there will be uh, d lambda y small d, right? And presence
Yes,
of
sir.
this one, there will be also d lambda by d, and
By
then
small d,
okay.
and then the yeah.
So lambda should be there, right?
Yes, sir.
So but lambda is not coming here because we are considering the central fringe, change from central fringe. Okay, so that change is directly given 0.5, and for absence of mica seed, this by n equal to 0.
Yes, sir.
So that's why this lambda is not coming. So you can just directly write this, and then you can find. So you are getting this 1 micrometer, right?
Yes, sir.
So this is the only correct answer.
So, in a question where we would not be dealing with the central fringe, then we would have to use lambda.
Yeah, that is my question. That is like, according to concept, there should be lambda, because
Yes, sir.
in both cases you have to find the part difference. Okay, there,
Yes, sir.
and you are comparing the same fringe. Okay, then there will be no lambda, I think, because if
All right. Yeah.
central fringe will be shifted right, then all the fringes will shifted by the 0.5. Only that difference will come when you remove the mica seed and input the mica seed.
Got it, sir.
Okay, so this is the main concept of having the measuring of thickness of some seed using double slit experiment.
Yes, sir.
And question 10 is, white light interferometer is mainly used to determine the polarization of light, to determine the position of central fringe, to determine the phase of light, or none of these.
To find the position of central fringe.
To find the position of central fringe.
Central.
Yes, that is the
So that's similar to basically the previous problem, right,
okay.
sir?
Yeah. Now you tell me what topics are covered in the current week.
So I've only done half the lectures in week 5, and for that we've got into Newton's rings. But before that, we were mostly dealing with interference of by division of amplitude. So division of waves we've done before in class 12 and everything, but in undergraduate we haven't done interference of division of amplitude and thin parallel films. So Heidegger rings and Poisson. I'm sorry, I'm forgetting the names, but different types of interferences.
Yeah. So number one, different types of interferometer, right?
Yes, sir.
And also thin film interference
Yes, sir.
you are talking about, and other thing what you said.
Uh, and then Newton's rings and Michelson interferometers come, but I haven't done that yet.
Okay, Newton's ring and yeah. So
Michelson
in
interferometer.
different type of interferometer there are, see, one is Michelson interferometer, one is Fary-Perot interferometer, Fary-Perot, and there are 4 or 5 types of interferometer. Okay,
Okay, sir.
one more thing in interferometer is there are 2 types of interference. So can you tell me what type of interference is happening?
Um, by two types of interference, do you mean like different types of fringes that are formed?
No, using different property of the light.
By by division of amplitude or by division of
Yeah,
the wavefront.
yeah.
Okay.
So that we know what is the interference. Okay, and we also calculated in the previous things what type of the light we need to interfere and what type of phase and all these things we have to maintain for the interference. Okay,
Yes, sir.
1 second. So in double slit experiment, just we start from here. So here we are using one source. Okay, and then it is split in two. So what you called it?
This is wavefront splitting.
Yeah, wavefront is splitting, right? 1 second.
Yes, sir.
So here one wavefront is coming like that, and this wavefront is only splitting. Okay, so
Yes, sir.
one of interference we uh, read division of wavefront, right? And another thing is division of amplitude.
Yes, sir.
So in thin film, what we read? We have, sorry. So in thin film, what is happening? the light is coming from here, right? This is
Yes, sir.
incoming light, and some are partially reflected back, right? And some of partially refracted. Okay,
Yes, sir.
and this light again from here, reflection
Will
happens, and
and then
again
it will be parallel to the.
reflection. Okay, so at this point, what is happening? Division of amplitude.
Amplitude.
So all these type of like thin film interferences, division of amplitude. Okay,
Amplitude.
so what is the part difference between these two light? If you raise this
So that will be
extra path,
calculated with the incident angle or
yeah,
the
extra path, why this one is, if this is D, okay, so incident angle is theta, then this is also theta,
yes,
okay,
sir.
and if this is theta and this is theta r, consider, so this is also theta r, and this is also theta r, this is also,
So 2d cos theta r
yeah,
into the refractive
d
index
cos theta r, आगे,
and the refractive index as well.
yeah, refractive index is also that 2 and d, 2 and d cos theta r will be, right,
Yes, sir.
and this should be equal to m lambda.
Yes, sir. For in order to get fringes.
And what is the phase difference happens
Uh, Due
rare,
to
rare to dense medium, dense to rare medium, that we have to
that will be by pi.
that is by pi, right?
Yes, sir.
So this pi is corresponding to 2 pi by lambda, sorry, lambda by 2 pi into pi, this is corresponding to lambda by 2, so you have to like something like that
Yes, sir.
to write.
But since it will reflect. I just had a doubt because I thought it will the pi by two will add up twice, right? Because it's going into the medium and then coming out.
No, 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 I am saying that you are observing interference here or interference here, it depends on equation, you have to consider different equation.
Okay, sir.
Interference
Got it.
happen in this region also, in this region also.
Okay.
Okay, so see, this is dense and this is rarer. Okay, so this ray is happening reflected with the dense medium, from the dense medium, right? So this has associated pi by 2 phase difference,
Yes, sir.
right? And from here this light is reflected from the rarer medium, interface from the rarer medium, right? So
Yes,
this
sir.
will not have any phase difference, the additional phase difference we can say, and in refraction there is no phase difference.
Okay, only in reflection.
Yeah, only in reflection. So this, in these two, this additional phase difference we have to consider.
Okay, sir.
Okay, if you are considering the light interfering here only, like in this region, then again this will be coming from here to here, right? And then again, so these two ray will be interfered, right?
Yes, sir.
So if you consider in this case, so here will be the additional, here is also refraction. Okay, so no phase, additional phase difference, here is also refraction, no phase difference, Here is reflection but from rarer medium, so there is no additional phase difference will come here also. And here is also again reflection, right?
Yes, sir.
So there is no uh, meaning to consider extra phase difference in refracted light interference. If you are considering the reflection interference in reflection light, reflected light, then there will be one additional phase difference. Understood?
Yes, got it.
You can see the videos, and sir have, I think, derived in detail. But here I am just only the concept which you have to consider there. Important thing is there, right? That additional
Yes, sir.
phase difference. So this is about the thin film interference. So this is plane wave, right? Plane refractive index. Now I,
Yes, sir.
if I, so what is the uh, I can say fringe pattern. What is the fringe pattern in this one? So here I am also telling you one concept. I told you that the fringe pattern will follow the path of the constant part difference or constant phase difference, right?
Yes, sir.
Okay. So here the part difference or phase difference is coming due to which thing? Thickness, no?
Yes, sir. The thickness of the film.
In this one, part difference is this one. Then in part difference, one is refractive index is coming, one is d is coming, right? And theta r will be same for all the things, right? This is the constant,
Yes,
theta
sir.
r is constant relation, n1 sin theta equal to n2 cos theta, right? Then
Yes, sir.
the constant thickness of the thin film is the constant fringes, the pattern of fringes. So using pattern of using seeing the fringe pattern, you can qualitatively can tell कि which surface is more rough or more plain or more smooth. Can you tell me? If I give you two different roughness of the surface, so see by seeing the fringe pattern, you can told tell us how which one
Yes,
is
sir.
more
Because
rough.
the thickness will like keep differing,
Yeah,
right?
roughness.
And in
So if thickness variation is more, the fringes will be more distorted, right?
yes, sir. And there'll be uniform fringe pattern in a smooth
A smooth surface.
film.
So this is qualitatively you can tell कि this surface is more rough and this surface is more smooth. Okay, by seeing the fringe pattern. But if you can calculate the fringe width and wavelength, all you know, you can also tell what is the roughness of your surface.
Yes, sir.
Okay, so there are many in surface profilometer depending on this interferometry. Okay, so you can hear about 3D optical surface profilometer. You can search about this one. So in this one also, what will happen? Light is coming from one path. Okay, we will have one beam splitter here. It will split your incoming light. Light is coming to your surface, and another light is coming in the straight direction. Okay, so what we will do, this much our reference surface, which we will have the very smooth, whatever how much smooth we can do, that we have our reference surface. And light is coming from here and light is coming from here also. This is your sample. Okay, so light reflected from here and coming from here will interfere at this point. Okay,
Yes, sir.
so this point, whatever fringes we will have, this is due to the roughness difference between the our uh, reference plane and our measured sample. Okay,
Yes, sir.
so this 3D optical surface profilometer is work on this concept only. We have some
Okay.
surface reference, and we have some unmeasured surface
Control.
reference. Okay, so this is one way of using the application of this interferometer only. Only simple interferometer. Okay, and different type of interferometer, I can tell you the very basic and what the difference between all these things. One is Michelson interferometer. So in Michelson interferometer, the basic schematic diagram I can, if I can make, so our incoming light will come from here. Okay,
Yes, sir.
then we have one beam splitter here. Beam splitter, you know what is beam
No, sir.
splitter?
I haven't done the practice.
Okay, then you can ask me what you are saying like that, because I used
Okay,
some
sir.
kind of beam splitter, so I found it very easy if someone said beam splitter. So beam splitter.
Okay.
So the name is beam splitter. That it divides the, it splits the beam. Means beam splitter is of many type. One is 50-50 beam splitter we call. Okay. So 50-50 term is used when this beam splitter uh, divide your incoming beam in two beams with the equal intensity. Like if I is coming, I is here, so I think I just say that this is your beam splitter. So what will happen, one light is coming directly in this direction, one light is will be uh, reflected from this surface and going to this one. Okay, so the intensity of both light will be I by 2 and I by 2. Okay, so this is the
Okay, sir.
functioning of beam splitter. If we are saying 50-50, if I am saying 90-10, means 90% will be transmitted, 10 will be reflected, and this is giving like that R ratio to T or T ratio R. In both way you can say 10 ratio 90 or 90-10. Okay, but they will specify कि R ratio T है कि T ratio R है. Okay, so if
Okay.
90-10 R ratio T means reflected light is this one, transmitted light is this one, so this will be 10%, this will be 90%, like
And
that.
so how is it physically split in a controlled ratio like this?
Okay, so I can tell you something. If we have one surface, right, like this is your mirror. Okay, so how the mirrors are made, do you know?
Not really, sir.
Presentation is off. Is my presentation is off?
I can see it.
Yeah. Is my presentation is visible or not?
I can see.
You can see my okay. So who is this? Kaniyappan G Kaniyappan. Hello. I got the message presentation is off. And Sudham, can you see my screen?
Yes, sir.
Okay.
So somebody else was starting his presentation and that was put off.
Okay. Okay. Okay.
Thank you, sir.
Okay. So the mirror is uh, see whatever our silica or SiO2 or silicon is there, or mirror we lead. Okay, so in mirror in back side there is some polish. Okay, this is called silver polished mirror. So अब now if we polish very thick layer, then nothing will be transmitted here, all will be reflected. But if it is partially polished, then some of beams coming directly transmitted and some of reflected. Okay, so one
Okay,
method
sir.
is doing this one. This is very coarse way, but in this one there is some type of cement is there. So when there these two triangular are added with some cement, and this cement is also uh, so the thickness of this cement we can control. According to that we can control the reflection and transmission of the beam splitter. Okay,
Okay, sir.
yeah. So in Michelson interferometer we have one mirror is here, this is mirror. Now this is not beam splitter, and one mirror is here. Okay, so the light is coming from, now I have to change my this one. So the reflected light from this mirror will be coming to here. Okay, and it will reflected in this direction and reflected transmitted to this direction. Okay, so
Yes, sir.
we don't need this one, so we will not talking about this ray, we are talking about this ray. Okay, and similarly the ray coming from reflection from this mirror will go, it will go in this direction also and this direction also. Okay,
Yes, sir.
you got it. So we are not talking about this direction because here our beam, our light is also coming. If we will
Yes, sir.
observe interference pattern here, our beam will be blocked. Like if you see my
Yeah.
screen here, then there is no light coming here, there no light.
Yeah. Yeah.
So our observation plane will be this one. Okay, so if this path, see this path is same, right? Here delta x is equal to 0. If this one is x1, this is x2, then x1 equal to x2 means equal path difference, means zero phase difference. Zero phase difference means
Zero phase difference means
only the central,
ma-
only maxima will be there, right?
only maximum will be there. Intensity maximum. Yeah.
Yeah, and if we put some kinematic mount here, okay,
So what's the kinematic mount?
kinematic mount is we have some type of mounts, we can displace it like that. Okay,
Okay, so got it.
basically we want to change the distance of this mirror from this beam splitter. Okay, so we have some stage, it can move here. So the now this x1 minus x2 will be some delta x. Delta x the displacement of this mirror. Okay,
Yes, sir.
like it, let's say it is coming from here, so this displacement is d, so this delta x is equal to d. So if this d equal to is some m lambda, then this fringes will be changing here. Are you getting my
Yeah,
point?
got it, sir. Yes, I got it.
Yeah, so this is something like, this is also explained some way कि this mirror is going to this one, and maybe this is the its mirror image of this mirror is at the same point. If you are displacing this mirror is something like that. So you can consider one way is coming from here, one ray is coming from here, like that. But you can also very simply say this is, if this distance is x1, this distance is x1, if these are both equal, then this above this point all paths are equal, so difference will be in this ray and this point, this ray, right? So this is known as
Yes, sir.
Michelson interferometer. Okay, and all the path, what should be the path difference, what is the, what it is called, maxima condition or minima condition, all these are same as we read before from interference condition, but the arrangement of this Michelson interferometer like this. Okay,
Got it, sir.
got it. Okay, so similarly, if we talking about Fairy parrot, this is called Fairy parrot Etelson also, Fairy parrot cavity also. Okay, so what is happening here? Here we are taking two parallel mirror. Okay, let's say its reflectivities are 1, its reflectivities are 2, or we can say this is 95% and 95% reflectivity is there, means 5% is transmission, and that we can control by the polishing only. Okay, am I audible?
Yes, sir.
Okay, so if the light is coming from here, let's say this is E, electric field amplitude E, then if relativities are, then light will reflected back from here also, and then reflected back from here also. Okay, so this, whatever light is coming from here E, this E1 will be R E2, sorry, R E1 E2, and here will be E3 equal to R square E1. Do you know how can I write this? Hello? Okay, so one round path will be, let's say the distance between these two is small d. Okay, so light is in one round. What is the phase difference? Delta x. This will be d, and again यहाँ पे आया, then is 2d, and is the path difference, path. Okay, so if this delta x will be something m lambda, means they will be constructively interfere. Okay, so we will made this condition from this fabric parrot Etelson, and you can see in the more detail in the search video, or I can tell you if you have some problem of understanding that derivation or whatever sir has said. Have you understood? Hello? So today I just solved one tutorial and I discussed about Michelson interferometer and some thin film interferometer and little bit about fabric arrow. Okay, so if you have some doubt you can ask me within this one, or we will stop here and I will come again in next week with some new topics and one new tutorial. Okay, are you fine with this?
Yes, sir.
Okay, thank you.
Thank you, sir.